Alright, we are back, and it's Chapter 9 today. And so Chapter 9 talks about these things called rational functions, and I'd like to introduce that to you today in section 9.1. And then I remember, well at least you should remember, looking at transformations from Chapter 1. I think we did that in chapters, 4, 5, 6, and everything else in between. So that transformation stuff is going to come back again. I hope that's not going to be too much for you. So, to begin, let's recall what a rational function actually is. You did this in grade 11, and if you don't remember, let me tell you. A rational function is just any function that can be written in this form, where you have a polynomial in the numerator, and also another polynomial, which I call q of x, in your denominator. Notice p of x and q of x are both polynomial expressions. And then because this is like a fraction, we have to also put on this restriction, or the non-permissible values. We have to make sure that q of x, the denominator, can't be 0. Some examples that you probably saw in grade 11. Well, remember this. Y equals to 1 over x, the reciprocal function. That's also a rational function because it's a fraction. Perhaps you saw something like this, where you have x over, let's say, x squared minus 3. Well, polynomial over polynomial. Maybe something even more complicated, like a quadratic on the top, and maybe another quadratic on the bottom. Right? Lots of this interesting kind of stuff. Okay? So, there's many, many more, but I don't want to waste your time doing that. Also, once again, how I told you earlier, recall from Chapter 1 these parameters a, b, h, and k, and how they change the function, right? Well, there's a mistake here. The effects of changing parameters in the, I should say, cross this out and say rational function. Oops, my bad. That's where you copy and paste and you forget to change, right? Well, once again, this whole parameter and all this shifting stuff is the same as what we've done before. So I don't want to go over it with you again, but here it is for your benefit. Hopefully you know this stuff by now, and if you don't, well, here's another chance to redeem yourself. Okay? We're going to do the same thing here. Once again, that idea of BERT, where we do the basic function first, then the expansion compressions, then the reflections and transformations. Well, sorry, not transformations, translations. Well, that applies here too. Okay? Now, once again, one of the rational functions you learned how to graph in pre-calculus 11 was of this form, y equals 1 over f of x. This was called the reciprocal function, because 1 over just meant the reciprocal. We did f of x, and it was a linear function, so you saw something like this, or something like this, quadratic. Okay, we're going to look at that again today, but we're going to expand our exploration by not just graphing those ones, but also some more complicated functions that can be made up of p and q being monomials, binomials, or even trinomials. So, are you ready? Even if you're not, too bad. Let's begin. Turn the page. And our first example here is I want you to graph out the function y equals to 6 over x. Okay? And I'm going to ask you to discover some interesting characteristics about this graph and fill in that chart on the bottom there. And then afterwards, I want you to use transformations to graph out this other function, y equals 6 over x plus 3, then take away 2, and then see what kind of interesting characteristics that one has. Alright? But let's deal with y equals 6 over x first. I'll use blue for this graph. And notice I already started a table of values for you, so what I'd like you to do right now, please, is plug in the values of x, and then calculate the values of y. Okay? You do that on your own, I'll do that on my own. We'll race and we'll see who's faster. Okay? Go. Divide by a half. 6 divided by a half. Oh, that's multiplying by the reciprocals. That's 12. Okay. Ooh, 6 divided by 0.1. That's like negative 60. And 6 divided by 0, we can't divide by 0, so that's just this thing called undefined. Alright, let's keep going. 0.1, well, I guess that's just the same thing as negative 0.1, just positive. So these numbers should be the same as the ones I just did before, except positive. Done. Did you win or did I win? It doesn't matter who won, as long as we learned this stuff well. So, I'm going to ask you now to actually plot these points, and let's see what happens, okay? See if you can sketch out the graph of y equals to 6 over x. Here we go. Negative 1, negative 3, negative 2, 2, negative 3, 1, negative 6. 0.5 is like negative 12. That's already off the chart. And then 0.1 is negative 60. So it goes really, really down negative. So I'm thinking the graph probably looks something like this. Woo. Okay, and then at 0 it's undefined. I don't know if you remember from last year what we did with this undefined thing, but that was what we call the vertical asymptote. And then to draw that in, we just drew a nice dotted line at, in this case, x equals to 0. Graphing all the other ones, 0.1 is 60, way up there. 0.5 is 12, that's still way up there. But 1 is 6, 2 is 3, 3 is 2, 6 is 1. And you get the idea that the graph looks something like this on the other side. Well, there you have it, ladies and gents. Here's y equals 6 over x. This is a reciprocal and also a rational function. I'm going to ask you to please take a look at the chart underneath and actually fill that out first before we go ahead and try the more complicated graph. Okay? Non-permissible value, that's the NPV, or where it's undefined. That's right, x cannot be equal to 0. Now, this is kind of interesting. It says the behavior near the non-permissible value from the left. Behavior meaning what happens to the y value. Okay, so behavior, what happens to the y value. Okay, when x approaches this NPV from the left. Now, for those of you taking calculus, I'm going to show you some calculus notation. You don't need this, but why don't I take this opportunity to do so? This idea of the behavior is like something called the limit. And I want you to approach x, or x has to approach from the left. Now, notice the NPV value is 0. From the left means it's from the minus, so 0 minus of the function. So if you're curious what that means by the graph, I'm saying, well, if you were a little ant traveling on this curve from the left, so watch, from the left of 0, what does the y value get closer and closer to as you do this? It's really, really down, really, really low. We would call that negative infinity. So our y value here approaches negative infinity. Okay? Now, behavior near the NPV from the right. Well, if I want to use that calculus notation, this is the limit as x approaches to 0 from the right, and we use a plus sign. If you go back up to your graph, what happens when it comes from the right? Well, it looks like coming from the right, it goes higher and higher, 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 and we would call that positive infinity. So let's write that in, please. Y goes to positive infinity. Here it says the end behavior when x is near infinity. So what I'm saying here is find the y value, and I'll use the calculus notation if you want, as x approaches to infinity. That means what happens when x is really large. And if I look at the graph, I'm talking about this stuff over here, and it seems like it gets closer to 0. Now, before I move back and forth, just to let you know, our next question is what happens to negative infinity, and it looks like it's also approaching 0. Okay. So here I'll say y approaches 0 when it's near positive infinity, and then y approaches 0 also when it's negative infinity. And the notation, just for you calculus crazy people, is negative infinity f of x. Okay. What's the equation of the vertical asymptote here? Yeah, that's the non-permissible value. So the equation is not x not equal to, but x equals to 0. And can you tell me if there's a horizontal asymptote in this picture? If you look back up here, can you kind of see that there's a horizontal asymptote? A horizontal line where the graph gets closer and closer to but doesn't touch? How about if you said the line, the x-axis here, which is the line y equals 0? If you said that, I'd be like, I totally agree with you. And so let's write that down. And then finally, the domain and range. So what happens there? Well, if you look at the graph, the domain seems to be all real numbers. Except for what? That's right, except for our asymptote, or our undefined or non-permissible value. X can't be 0. What about the range? Yeah, you got it. Same idea. Y is all real numbers, but y can't be equal 0. Okay? Alright, so I hope you got an idea of what's going on now with the characteristics. Let's go back up, and I'm going to ask you now to try to graph the other function. This one looks a little bit more complicated, but not to worry, because you know your transformations from chapter 1. I'll do this one in red, by the way. Can someone tell me what transformations occurred to go from the blue to the red equation? If you're not too sure, look back at your first page. But in this case, you notice you replaced x with x plus 3. That means you did something horizontally, and you shifted it, I believe, 3 units to the left. Right. No, left. Yeah, correct. Left. And that minus 2 would be shift also down 2 units. Now you can go ahead and make a table of values again, but I'm kind of lazy, so all I'm really going to do to help me sketch out this graph is I'm going to shift the actual asymptotes, and that will give me a good indication of where things should be. Okay, so think about it. If I shift my vertical asymptote of x equals 0 3 units to the left, it'd be now here at negative 3. And if I were to shift the horizontal asymptote at y equals 0 down 2 units, it'd be now at y equals negative 2. And if I really wanted to get this accurately done, then I think every single point I have should go 3 to the left and then 2 down. So, for example, this one here, that was at negative 3, now it's at negative 6. 2 down for that would be negative 4, so right about there. And I can just shift all of these, but I'm going to be kind of lazy. I know it's not good, but you get the idea. The graph now looks like this, okay? On one side. And I guess here I could shift. I'll take this point, go 3, and then down 2. Here's another point, 3, down 2, 3. Sorry, 3 units left. 1, 2, 3. Down 2, 3, down 2, 3, down 2. And I think you get the idea what the graph looks like here. Okay? So the one in red is y equals to 6 all over x plus 3. Then take away 2. And if I'm going to now, I'm not going to be if, I'm going to ask you actually now to fill out the characteristics of this graph. And I want you to do this one on your own. Okay? Alright, you go try, stop the video, try it, come back, play it, the answers will be there. Okay? Now seriously, try this. Go. Okay, if you got all these right, give yourself a pat on the back. And if you got these wrong, well, go fix it and figure out why. Alright, so that's an easy one. I shouldn't say easy, but simpler one. Now let's try graphing a rational function with a linear expression in both the numerator and the denominator. Alright, let's go. Alright, let's take a look at page 3. Alright, here we go, page 3. I'm going to ask you to change something here. Instead of y equals 2x plus 5, let's change it to y equals 2x plus 6. Thank you. Just makes the numbers easier. In this case, I want you to graph this function, identify any asymptotes, and also the intercepts. Now, to do this, because it looks kind of weird, I want you to try to change it in that form that we saw in the previous example. Okay? And now to do this, we have to go ahead and do some long division. So we'll do some long division. And we did stuff like this before in chapter 3. So if you forgot, go back to chapter 3. So I'm going to ask you to do long division. I'll set it up as x minus 1. And you're going to take the 2x plus 6 and divide it into that. This is like that polynomial division. Yeah, chapter 3 stuff. Factor theorem. This is where you ask yourself, x times what gives you 2x? And I hope most of you say 2. And then you go 2 times x minus 1, which becomes 2x minus 2. And then you subtract. And then 2x minus 2x is gone. It's 0. 6 take away negative 2x is, 6 take away negative 2 is 8. And so therefore, you've actually rewritten this function 2x plus 6 over x minus 1 as 2, that's your quotient, and then plus 8 all over x minus 1. And if you want it in that type of format here, I'm going to say now y equals 2, and just going to rearrange the order, 8 over x minus 1 plus 2. Okay? Now, right away from here, to try to graph this out, even without doing a table of values, you should be able to do a quick sketch. I would always say to you, identify the asymptotes first. Okay? And if you can find the intercepts, even better. Okay? Asymptotes. Let's do the obvious one. The asymptote that is vertical. What will that be? You look at the denominator. That's x minus 1. So your vertical asymptote is where x minus 1 can't be equal to 0, or x can't be equal to 1. I will start by drawing a nice dotted line there. Now, if you're curious about your horizontal asymptote, hopefully you saw from the previous example that your horizontal asymptote is just that number that's hanging outside there, the 2. So y can't be equal to 2, and I'll draw that in as well. Okay. I also said intercepts, so we can find the X-Intercept and Y-Intercepts. Let's do that. So to find the X-Intercept, the idea is you let y equal 0. So 0 equals to 8 over x minus 1 plus 2. I will do some quick algebra. Negative 2 equals 8 over x minus 1. Go ahead and cross multiply or something, whatever you wish. You get negative 2 bracket x minus 1 equals 8. Divide both sides by negative 2 and solve by adding 1. I believe x equals to negative 3. Okay. If you're looking for the y-intercept, I guess I can do that too. Quickly now find the y-intercept. That is where you let x equal 0, so y equals to 8 over 0 minus 1 plus 2. That's just negative 8 plus 2, which is negative 6. So I guess there's a dot here. And I can already guess what the graph looks like over here. Going through 6, crossing at 3, getting close to the horizontal asymptote at 2. And the other side, probably the same idea. Let me move up a little bit. Okay, something like this. Whee! If you want to be more accurate, you can plug in some numbers. If you plugged in, let's say 3 minus 1 is 2 for the x here. 8 divided by 2 is 4, 4 plus 2 is 6, I think. So 3 is actually equals 6, so oops. Maybe my drawing not so accurate. So once again, all I'm doing is just plugging in x values. Okay, you can plug in other ones. If I plug in 5, what do you get? 5 minus 1 is 4, 8 divided by 4 is 2, 2 is 4, so 5 is 4. You get the idea, but, you know, there you go. Okay, done. All right, example number 3 is this, where I've changed it up. I'm going to ask you to find the equation below when I give you the picture. Now once again, just like in the previous one, what helped me find this out? It's my asymptotes. So let's see if you can identify them first of all. Yes, a vertical asymptote as x can't be equal to -2. And as a hint, that affects the h. See if you find a horizontal one. It looks like here it's not drawn, but it looks like it's -4. So your horizontal asymptote is y can't be equal to -4. And yes, that should affect the k. So right away, you have already solved for 2 of the unknowns. You have now x minus -2 minus 4, or I'll simplify this to a over x plus 2 minus 4. However, you still need to solve for a, so how are we going to do this? Well, once again, x and y are coordinates on this graph. Can you find a nice place for a nice set of coordinates? I see one. Do you see one? How about this one right here? This seems to be the point 1, comma, -3. And you can pick other ones if you wish, but that one seemed nice to me. So I'm just going to ask you to plug in 1, comma, -3, and hopefully you can solve for a. Not hopefully, I know you can. So do it. -3 equals to a. 1 plus 2 is 3. A over 3 minus 4 equals -3. Add 4 to both sides. A over 3 must equal to 1. Therefore, a equals to, oh yeah, 3. And so ultimately, therefore, your equation is y equals to 3 over x plus 2 minus 4. Ta-da! Alright, we're almost done. Turn to the next page, and I'm going to ask you to try to graph some more stuff out. Okay? I'd like you to graph out 1 over x squared, and I've already given you a table of values to do so, so I want you to try that one first on your own, and then I'll come back to discuss the other two. So maybe this one I'll use for blue. Here I'll use red. And last but not least, let's use green. Okay? Oops. Hey, green. Yeah, green. Okay? You do this first on your own. Okay? Y equals to 1 over x squared. Table values, do it. You should be fine. Okay? Go. Stop tape. Go. Alright, let's take a look at some of these numbers. Blue. Remember, -5 all squared. Negative times negative is positive. Okay? Excuse me. That was me burping. Alright, if we can graph these out, -5 is 1/25, really small. -2, 1/4, still kind of small. -1, 1, -0.54, and then woo, way up. So I hope you can see the graph looks like this. Woo, oops, that doesn't look very good. Let's try again. Dun 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 dun. Yeah. Okay. And then the other side is the same, right? So 0 is undefined. I'll draw in my vertical asymptote. And then 100.5 is 4. I wish I had music, hey? Background music might be interesting. Or distracting. I don't know. There you go. Characteristics. Let's quickly fill those out too, okay? Non-permissible value. Of course, x can't be 0. Behavior from the left of the NPV, y seems to approach positive infinity. From the right, in this case, it also seems to approach positive infinity. And behavior, that means when x is really big, it looks like the y value approaches 0. Same thing happens when it's negatively or negative infinity to the left. Equation of the vertical asymptotes, well, yeah, well, that's x equals 0. How about the horizontal one? Yeah, it seems like it gets closer and closer to the line y equals 0. You're right. And domain and range, yep. Okay, so domain is x is all real numbers, and of course, x cannot equal to 0. Range, though, however, this time is not all real numbers. It looks like everything is positive, and that's because of the x squared in the denominator. So your range is just y is greater than 0. Good. Now, how do we draw the next one? 2 over x squared minus 8x plus 16. Let's go back up here. I want you to take a look. Can you see something interesting about the denominator here? Yeah, I know it's a trinomial, but can you factor it? I hope you can. Two numbers that multiply to 16 and add to -8. Yeah, it's x minus 4. So this is the same thing as 2 over x minus 4 times x minus 4. Well, what is that? That's y equals to 2 over x minus 4 all squared. Yeah. And if I ask you to compare that with the blue graph, the 2 means it's a vertical expansion by a factor of 2. So you're stretching it vertically. And the x minus 4 means you shift it 4 to the right. So vertical expansion by 2, 4 to the right. And so now I'd like you to graph that out. You can make a table of values, but let's just do a quick sketch. I'm going to ask you to graph it out with a sketch. Have an asymptote at 4. And then the vertical expansion by a factor of 2 just stretches it really more thin. So I'm just going to draw it a little bit more thin. And we're done. There's your sketch. Okay. I'm going to ask you now to go back down and do the characteristics for this one. Okay, now stop tape and try it on your own. Then come back and play the tape. Yes, you'll see many things are the same except the vertical asymptote has changed. So of course your domain also changes, but nothing else changes. Alright, one more. Back up to the top. Oops, I went too far. Okay, How about the last one? Now, you need to identify all the different transformations that have occurred. Okay? If you do that, life is good. I'm going to rewrite this over here as y equals to negative 1 over x plus 5 all squared plus 6. I think in this format, it's a little bit easier for us to see the transformations. Okay? That negative, yes, is a reflection in the x-axis. This x plus 5 means you shift it 5 to the left. And the 6 on the side, of course, means you shift up 6. So remember, what we do here first of all, ladies and gents, is we do the reflections, and then we do the translations of 5 left, 6 up. So if I were to do the reflection on the blue graph, I'll just quickly sketch it. Would look probably something like this. But then I have to shift it 5 left and 6 up. So watch, I'm going to shift the asymptotes first, 5 left, 6 up. And then I can modify my green graph here. And instead of having it down here, let me erase them. Let me erase them. And draw them up here. So, woo. Woo. And there's my answer for the third one. Once again, stop tape. I want you to try to do the characteristics on your own, and then come back and check your answers, please. Okay? Then we'll be done. Don't be lazy now. This one's the most interesting of them all. Did you switch the sign here for the range? Remember, reflection. Done.